average temperature. And that'll do it for this lecture. So thanks, temperature. We will start with the INDC commitments of one of the tutorials during the climate conference. You can see the individual commitments in the table in the bottom left, and in the chart above, you can see the energy CO2 emission curves of the different countries that go along with these commitments. On the right, you can see how the temperature trajectory with these initial INDCs compares to the business as usual scenario. And below it states that by 2100, these emission reduction commitments are expected to result in a temperature increase of 2.8 degrees Celsius relative to pre-industrial levels. Now, in addition to these default charts, the C-ROADS application, the model that you use, has a bunch of other charts, but these are the ones that we have been focusing on. So, for example, you can look at the energy CO2 emissions per capita, which nicely highlights that under this scenario, even though China and other developing nations are the biggest emitters overall, the US and other developed nations have the highest per capita emissions all the way to 2100. The light blue curve shows nicely how the economy of China rose in the early 2000s when the per capita emissions quickly caught up to the developed world. There are many other interesting charts that the model can produce, so if you're interested, you should definitely check out the model and play with the numbers yourself. Let's go back to the overall annual energy related to CO2 emissions from each country or geopolitical region. Now, the question we want to address in this short lecture is, why is the temperature still going up at the end of the century, despite the fact that all the regions have committed to decent reductions, and in 2100, the overall emissions are only about 60% of what the emissions are right now? On the right, you can see that we have bent the temperature curve away from the business as usual scenario, but it's still pointing up. So to answer this question of why the temperature is still going up, let's look at emissions slightly differently. Instead of looking at the country's regions individually, let's stack them. And this shows how much energy-related CO2 emissions we have globally in total. And the slivers of each country or region give you an indication of how much of each of them are contributing to the global total. Now, we also can look at how these contributions change over time with a given scenario, with any particular scenario we run. So here, you can clearly see how the emissions the emissions in 2100 are lower than in 2020. So overall, the emissions have gone down. You can also see how the country or region that contributes the most to the emissions changes over time. So first of all, it was the US and the EU countries in 2000, then China in 2020 and the 2030s, and then the other developing countries later in the century. Now, you might remember, I hope you remember, from our lecture on the alternative definitions of sustainability, that nature works in two well-balanced cycles: the fast biological cycle, that is driven by the energy we receive from the sun, and the slow geological cycle. And one of the issues of unsustainable societies is that they overwhelm these cycles by extracting massive amounts of material from the Earth's crust. Let's look again at the carbon cycle. We have looked at this figure in the very beginning of the course when we discussed cycles in general, so I hope you recall some of this stuff. The black boxes show reservoirs of carbon, because this is the carbon cycle, and the blue boxes label the different fluxes. So we talked about reservoirs and fluxes. So the black boxes are the reservoirs of carbon, and the blue boxes label the different fluxes that move carbon around. Now, our use of fossil fuels means that we have massively increased the flux from the Earth's crust up to the atmosphere, because we take the oil and fossil fuels out of the Earth's crust, and we burn it, and we send the carbon up into the atmosphere. But all of the natural fluxes that remove carbon from the atmosphere have generally remained similar to the levels that they were at before we started extracting all these fossil fuels. This is what Alex meant with the overwhelming the cycles in the lecture on the rules of nature. So when we talked about how you overwhelm the cycles. Quick side note here, what I just said is not exactly correct, but it's close enough to the truth for what we want to discuss here. The ocean has actually absorbed a lot of the emitted CO2 in our climate problem would be a lot worse if the ocean wasn't doing this. But in the ocean, the CO2 is leading to ocean acidification, which is another different problem. This graph shows the magnitude of the two fluxes. The total emissions are shown in gray, and the natural removal of CO2 from the atmosphere is shown in green. As you can see, the emissions are higher than the removal during the entire time that we ran these scenarios. So what does this mean? It means that despite the reductions that we made with the country's choices, we still continue to add more carbon to the atmosphere than gets removed by natural processes. And the concentrations of CO2 continue to increase. In the graph on the right, you can see that the concentration has risen from about 400 parts per million in the scenario in 2000, the year 2000, to about 600 parts per million in the year 2100. This concentration is more than twice of what it was during the pre-industrial times. So, to stop the CO2 concentration from building and to stop the temperature from rising, we need to bring the gray curve of the emissions below the green curve of the removal. Climate change educators have used a bathtub analogy to explain the situation. Our emissions are the amount of water that fills the tub from the faucet, and the removal of CO2 from the atmosphere is analogous to the amount of water that leaves the bathtub through the drain on the right-hand side. Now, as long as the amount of water entering the tub is greater than the amount of water being drained out, the water level in the tub will keep rising. The level in the tub will only stop rising when the water coming out is the same amount as the water coming in. And then to get the levels in the tub to actually drop, then obviously the water coming in has to be less than the amount of the water draining out. For the temperature to stabilize and potentially even drop again, we have to do the same with carbon fluxes. We need to get the gray line below the green line. Now, there are two ways of achieving this. The first way is to reduce the emissions. And so in this scenario, you can see that the emissions and the removal lines have come together because we dropped the gray emission line. And therefore, the concentration of CO2, the right-hand graph, levels out towards 2100. If we flip the right-hand chart, then you can see that the temperature levels out as well because it's directly linked to the concentration of CO2. Now, if we go back to the original one that we're working with, there's another option for stabilizing the temperature. And this is to increase the green line. That is the amount of removal rate from the atmosphere. So if we can remove more, raise the green line above the emissions, which is the gray line, then that's another way of stabilizing the temperature. So in order to do this, in order to raise the green line of removing carbon from the atmosphere, we need to find ways for removing that carbon from the atmosphere and permanently putting that carbon into a reservoir or a sink that's not the atmosphere or the ocean. Now, there are a number of ways that people have proposed to do this, and there are a number of ways to do it, but we'll only briefly touch on two of the options here. One of the ways is afforestation, as compared to the opposite, which is deforestation. So afforestation refers to the planting of new forests, and in areas where we did not have forests before. This works because trees absorb CO2 and then turn it into organic material, essentially the tree trunk, through photosynthesis. Now, new forests can expand the amount of carbon that is stored in the biosphere. More forests, more storage for carbon. There are limits to what can be done with this approach, but it is one of the possible ways. This is why we have the promote afforestation column in the C-ROADS model, although we didn't use it in our scenario, but you can add to it if you want to really look at what this model can do. Similarly, slowing down the destruction or the deforestation of forests, that also keeps carbon in the biosphere and prevents that carbon from being released into the atmosphere. And this is why we have the prevent deforestation column in the C-ROADS model as well. Playing around with the values in these two columns is interesting as well, but it adds a whole lot of complexity to the negotiations that we did in class, and unfortunately we don't really have time to go into those more depth conversations. But it is essential for you to understand the role of deforestation and afforestation. The other option to get the green line above the gray line is what's referred to as carbon capture and storage, where you use some form of technology to either capture CO2 at the source, for example, at a power plant, or you can chemically suck the carbon out of the air, and then store it underground in geological structures away from the atmosphere. So you're essentially, what we would be doing under those scenarios, putting the carbon back into the ground where we got it from originally when we dug up the fossil fuels. There are a number of technologies that are being pursued for making this happen, although to be clear, there is no carbon capture and storage that's available on any sort of practical level just yet. But there are lots of people working on it. And one of the pioneering companies involved in this work is Carbon Engineering based in Squamish. And so if you want to learn more about their work, you can take a look at their website at carbonengineering.com. So it's pretty interesting that it's so close to Vancouver that someone's really working on this. In 2019, the CEO of Carbon Engineering gave a TED Talk in Portland, Oregon. And here he explains the goal of his company. So that's another thing that you can watch. They're essentially trying to create carbon neutral fuels with the carbon that they suck out of the atmosphere. There's a link in the lecture below in the supplementary material on Canvas if you want to watch this lecture. And when you take a look at it, you'll notice that we're not the only ones using the bathtub analogy to describe what's going on. Let's wrap this up with the main take-home message. Reducing emissions is a step in the right direction, and a key step in the right direction. But to stabilize the average global temperature, we need to get the emissions below the removal rate for carbon. The only way the concentration in the atmosphere will actually stop going up is to do this, and this is what the bathtub analogy illustrates nicely. In addition to reducing emissions, we can also help our cause by increasing the removal rate of CO2 from the atmosphere, and we briefly discussed a couple of approaches for doing that. So I hope the information presented here helps you better understand the relationship between emission reductions and the overall global average temperature. And that'll do it for this lecture. So thanks for listening. We'll talk to you again soon. Bye for now.